please hit subscribe.
Hey folks, today we're going to try to simplify this limit here and express it into more familiar terms. So let's start. First off, we make a few easy simplifications. Right off the bat, we can see that we can distribute the exponent so that we have these terms, -1 raised to one of these exponents because they're just the sum here. And then when we do that, we can see that we have -1 raised to the second power, -1 squared, and this is just 1. We know that already, so we can just eliminate that from that expression and then rearrange the exponents and the terms so that we can factor out the terms that involve k, and we see that we are left with a sum of terms that involve only n. So we're able to separate k from n. And this is a good start. So we'll start from this for the next steps. The previous result to this slide. This is our previous result. Now we make the following observation. N factorial, that is this exponent out here, is always even if n is greater than or equal to 2. And we can see why that is true if we try to expand n factorial. Now, again, n is greater than or equal to 2. So if we do that, we have n times n minus 1, and this is by definition, all the way to 1. And if n is greater than or equal to 2, then this term here, this 2, is always going to be present as a factor. Okay? If n equals 1, then we don't have these terms here. We only have 1. So we don't say that it's even. But if it's greater than or equal to 2, if n is greater than or equal to 2, we always have the 2 there up to n, whatever n may be. All right? And so we know that -1 raised to the n factorial would always be equal to 1. Again, because n factorial is even. And this is only true, though, if n is greater than or equal to 2. And so we have this simplification here. This term here cancels to 1 only for n is greater than or equal to 2. And so what we can do is actually eliminate or separate the n equals 1 term. All right? And this is the result from the previous slide. And just before we separate the n equals 1 term, let us try to make a few observations regarding the limit as k approaches 0. We notice that this limit cannot make sense if we do not have values of k for values around 0. So for example, 0.01, 0.001. So if we do not have those k, then we really cannot define this limit. And the way we impose that those values be available is that we define k factorial instead of the regular definition where we just take the product of the natural numbers from 1 to k. Instead, we impose that k factorial be the gamma function. By doing this, we are assured that we will have k factorial even for k that are close to 0. Let's say 0.1 or 0.001. So this is to ensure that we will get that the expression makes sense for k around 0, very close to 0. All right. So if we do not impose that, then this limit just does not exist. And we also have to make the other condition true, that -1 is the complex number e raised to the j pi. So if -1 were treated as a real number, we will have a problem evaluating -1 raised to the k factorial, because -1 raised to some exponent could fluctuate between a negative and a positive number depending on the value of k factorial. And so to avoid that complication, we gotta impose that -1 is a complex number before we take the limit. All right, and so if we impose these two conditions, we have a chance of at least evaluating this limit. And in fact, we can say that k factorial, if we use the gamma function definition, you will see that this limit is actually 1. And likewise, this term here reduces to -1. And then, if we use this result, our expression here results to this one. All right, so we eliminated this bit here. We replace it with the negative symbol because it's -1. And again, we remind ourselves that this is only valid, this cancellation to 1 is only valid for n is greater than 2. And so for the next slide, we separate n equals 1 so that we could have a strictly correct form of this expression. So we just put here the result from the previous slide. And now we separate n equals 1. So here we have n equals 2 to infinity, and that's only after separating n equals 1. And this is for n equals 1. So it's just -1 raised to the replace n with 1. And so we have 1 factorial there, n with 1. So we have 1 there, n here is 1. So we have 1 there. So this is for the case of this expression when n equals 1. And whatever is left is for n equals 2 to infinity. And for that case, we can just remove this term because we know that it reduces to 1 for n is greater than or equal to 2. And so this is our term now, our expression now. And the next step is to notice that this sum here could actually be a familiar function if we have n from 0 to infinity instead of just from 2 to infinity. And so we try to complete this. So we add the terms for n equals 0 and n equals 1, and then we subtract those terms again. So this is for n equals 0 and n equals 1. So we added them here and we subtracted them here so that the subtraction and the addition cancel each other and they won't have an effect to the total sum. And so we still have this. Now we just evaluate these terms. So this term for n equals 0, this evaluates to just 1 over 2 factorial, and that's just -1/2. And this one, if we evaluate that, it just becomes 1 over 3 factorial. And we do, this is positive though, there's negative here and negative. And then we have one more here. And again, this one is from this term here. We simplify this into this. And when we combine terms here, we are left with the following 2/3. So this one, and this one, they all combine to become 2/3. And also, we already added the effect of this negative sign here. And this one here remains the same, except for the negative sign. We just put it here. And now, the advantage of expressing it in this way is that we see that this one is actually a familiar Taylor expansion. So this is that expression from the previous slide, and we notice that this is a familiar Taylor expansion of, in fact, sine of x. So So sine of x is just this bit here. And we notice that they are very similar. And if we replace x with 1 here, they will be exactly the same, this one and this one. And so we are forced to conclude that, in fact, our original expression is just equal to 2/3 minus the sine of 1. And this is a much more familiar form of the more complicated series that we had at the beginning. If you learned something new today, please help my channel by clicking the subscribe button and the bell for the notifications. See ya!